going to introduce the next speaker, because he's an ADIA Lab fellow. It's my great pleasure to introduce our next speaker, Torsten Hoefler. Torsten is a professor of computer science at the ETH Zurich. He's leading the Scalable Computing Lab, and he's also the chief architect for machine learning at the Swiss National Center for Supercomputing. I hope this works. He's an ADIA Lab fellow, so this is why it's extremely exciting to welcome him here to Granada, to our ADIA Lab UGR summer school. His research is at the intersection of AI and supercomputing, and Torsten has received a lot of prizes in his field. Most recently, the ACM Supercomputing Prize, the Gordon Bell Prize. I heard that's like the Nobel Prize for supercomputing. The Max Planck-Humboldt Medal, also very recently. So it's a great pleasure to have him here. I need to tell you, like from experience in Abu Dhabi, his sessions, his seminars are very, very well attended. Like usually there's standing room only. And the Q&A sessions with Torsten usually last as long as the presentation itself. So please use the opportunity to ask questions, as many questions as you would like. It's a great opportunity to have him here. And please join me in welcoming Torsten to our summer school.
I mean, first of all, I didn't say anything yet, so don't clap. Okay? So because you'll see if you want to clap at the end. Second, as she sets the bar high, I'm Torsten, so ignore what was just said. I'm going to talk about reasoning and sparsity in large language models. So this is actually funny because some people really like small language models, but I'm more like a large language model guy because, as she said, as Amelie said, we are working on very large things. So this talk, it's actually supposed to be a tutorial, not a talk. And I am super happy if you just go, and I'm not even going to slide 2, and you just ask questions. But I will start with the slides. And I will see. If there are any questions, let me know. I can go to a whiteboard setting and I can explain anything you want well, not anything you want. Don't ask me about bees and pollination and stuff like this. But anything that you can see remotely related to the slides, I can probably give you my take on it. But I will start with the slides. And first, I wanted to start with the sparsity in deep learning papers. Actually, one of my highest cited papers that I wrote a while ago. And if you look at this 2021, that's the funny thing. That's like ages ago in machine learning. I mean, if you see a paper from 2021, it's most likely completely outdated, which is partially true, but not for this one, because it's actually not a methods paper. It is an overview paper of what has happened and is very fundamental in nature. So this forms the basis of what I'm going to talk about. If you want to know anything more about anything deeper than what I'm covering here, you can just look at the whole thing. It is the longest paper that was ever published in the Journal of Machine Learning Research, and the editor still hates me for that. But I want to start a little bit earlier, 2021. In machine learning, that is the beginning of time. But actually in humanity, I want to start a little bit earlier. And some of you have seen that motivation before, but I still want to go and motivate you of what's happening right now with humanity, because we are at a new age where we are getting into as humans, which we probably don't know how to control, which we probably don't know what we are going to end up with in 10 years. And this is why you're here, because you want to understand how to use that reliably and in a way that you can control it. So I will give you more technical background of where these things come from. I am not brave enough to talk about reliability of these things, because knowing how they work, I do not understand how the reliability and interpretability of these things functions at all. I can give you my take, but I think it's extremely complicated. But let me start early on. So 2 million years ago, I know, this is going to be a long talk. 2 million years ago, humans discovered materials, right? So it was first stone, then bronze, then iron. And this is actually interesting if you think about it, because before that we were basically like animals. We did not use any tools. We discovered materials to make tools. And many of these ages in humanity were characterized by the fundamental material or fundamental thing that humans used, right? So materials was very early on. And then we know that we went into construction manufacturing. So we used these materials to build bigger things. We built bridges, we built carts, well, cars came later, but things like that, right? And then actually bigger things, big houses and stuff like this. So this is now getting a little bit further. Then came the Renaissance and then the Industrial Revolution. What was the Industrial Revolution? That was the major step in humanity, I would say, that we had so far. In my personal view, the AI revolution is going to be the second major step in humanity. And you and we are alive at the time when it's going to happen. Right? This is something that's very interesting. So the Industrial Revolution was really that we invented things like built from materials that could automate a gigantic part of our work. Because today we can operate cars. Before that, we had to operate everything with muscle power. After the Industrial Revolution, we had steam engines, we had gasoline engines, we had other engines that gave us extremely large power in terms of, physical power. So today, I, as a very frail human, I can operate a 700,000 ton cargo ship alone. Like 700,000 tons. No animal on this planet would even think about moving 400,000 ton objects. We can fly planes, we can drive cars. Okay, cars are not that heavy, I can still push it, but think about it, right? So everything changed. The fundamental thing that changed in the Industrial Revolution is that human physical strength became completely irrelevant. Any frail human can have power over a much stronger human by using machines. Think sadly about warfare, right? So we got to use tanks. So even the strongest human cannot fight a tank. So that is a fundamental change in human history. Okay? So what else happened then? Of course, we didn't stop then because that was all before our time. We were not alive when this stuff was invented. So then we moved into the age of technology, which was the atomic age. That was great, even more powerful materials. The space age, great. The digital revolution, and this is something where I want to stop a little bit because that's where I came online. So about 81 was my, when I came out of the womb of my mother. So still with the old way of being created. And that was another interesting way, because then we used computers. Like we started computers. Actually, shortly after, we realized that we can connect these computers. This was one of the bigger revolutions, not the biggest one, the internet. Like we connected all of these computers together. Now we can communicate over the internet. That's great. And then after a while, we realized that the internet, about 2015, so about now, we have collected so much data in that internet that we can actually use that data without understanding what all of that data does. Right? And that is now leading us to the point. So I want to leave you with that question, because we have the physical strength is already irrelevant. Today, intelligence and creativity is still relevant. Think about this. I'm not going to answer that question, but it's going to be very, very, very interesting. Right? And I'm convinced this is going to happen. Now, the interesting thing, I want to now give you a little example of what creativity in some sense means, and to rub it a little bit more in, because it's extremely hard to define what creativity and human intelligence actually means. Is human intelligence knowing what the capital of France is? Probably not, because any freaking language model can do it, so it cannot be human intelligence. Is human intelligence just emotional intelligence, understanding how other humans behave? Probably not, because unfortunately language models can do that better than humans today as well, than the average human. So now it gets interesting to even define what human intelligence means. But I want to go to an extreme case. I want to go to a game that is possibly the simplest game we have to understand. It's the game of Go. I assume everybody knows the rules of Go. It's very, very simple. You have two colors, white and black, and you're basically you have to surround the other player's stones with your stones. You have stones, you put them on a 2D grid, and you have to surround the other player's stones, and then you can take them. And then you fight for who has the most stones left when you run out of moves. Right? So it's a very simple game. You can explain this to every 3-year-old, no, maybe 5-year-old. It depends on how far you are. In about 15 minutes, and that kid will be able to play it. But at the execution, this game is one of the most complex games that humans can play. So the rules are absolutely trivial. Place stones on a 2D grid. But the strategy and the tactics in that game are extremely complicated. So there are world championships in Go, which are televised mostly in Asia. So we in Europe, we like football more. So you kick a ball, that's more of an ancient thing. In Asia, they like these kind of intelligence games quite a lot. So they look at it. It's actually, I'm not kidding, these are televised and millions of people watch these championships. So there was the 18 times champion of Go. And so that is a highly celebrated individual. So Lee Sedol is his name. And Lee Sedol is ingenious. He literally devoted his whole life to playing Go. He started at a very young age. He played Go. He's the most proficient Go player on the planet. And so what happened, unfortunately, he was beaten by a machine, which was very, very unexpected. And I would recommend all of you, there's a documentary on exactly that. It's a very, very well done documentary. How the machine beat Lee Sedol and what happened afterwards. That was live televised, and like all these people who watched were like, oh, that is getting interesting. But I want to tell you how it happened. Because it was always considered the hardest game to play. Chess was beaten much earlier. I mean, chess is machinized really easily. Go has a very large option space. But how does it work? So you have a board. Like, as I said, it's a 2D board. You put white and black stones on it. And you play by the rules that I just mentioned. But now we're all kind of computer scientists, so we want to understand how it works. So you model the state of the board as some starting state, in this case S00. So what you do is you ask some kind of function. I mean, you could ask a human, or you could ask some kind of computer, give me a possible move. So where do I place my next stone? Let's call this function pi. After you place that stone, you will get to a new state, right, that you can evaluate again. And now what you do is you ask that function pi multiple times with some kind of random, a little bit of randomness. Many people call this heat in machine learning. So you put some kind of random component in it that you don't get the same move all the time. So you get similar moves. Right? Then you ask this multiple times, and then you get m possible candidate states. So it's like you think when you play. I could do this, I could do this, I could do this, I could do this. Right? You can machinize this. You can ask a machine to propose these steps. And what you do then as a human typically, when you see all your possible options, then you think about which is the best option, obviously, because you can only make one move, right? And what you can do then as a machine, you can ask the machine to judge each of these new states that were just created by a move. How likely is my probability of winning when I'm in that state, right? And now we get probabilities 0.01, 0.00, and so on. So that's now relatively easy. So we have two functions, right? One function proposes moves. One function assesses the probability of winning if I'm at that state. And then what I do, of course, if I'm not totally stupid, I pick the highest probability of winning, because otherwise that would be pretty dumb. And then I do the same thing again, because of course there's another move I have to make. Of course, after my opponent made a move, but we'll do this. And then we assess the probability of winning again. And then we may realize that the previous move was a bad idea, because my probability of winning with that move previous, and then I have a limited choice of option is worse than the first one. This is typically something we humans don't do, because you can't do it in practice, because you can't backtrack. Like once you have made a move in a game, you can say, oh, I was wrong, let me correct this. But of course, in a machine, you can do it, right? You can go forward and backward. That's quite nice. And so then you keep playing this game. And this is exactly what the computer played against Lee Sedol. The computer was simulating all kinds of different options. This is why the computer can track back, because the computer was simulating until the end before the computer made the move. We humans, we don't simulate when we play chess. Okay, the expert players actually do simulate. If I play chess, I don't simulate. I just look at the game. I was like, yeah, it looks good. Let's move this here. I'm not an expert player, as you can tell. But in fact, expert players do simulate, but only 5 to 6 steps ahead, because the option space is too large. A Go player, so Lee Sedol was admitting to actually doing multiple dozens of sampling steps ahead. These computers can do hundreds of steps forward, right? But of course, they sample a very small number of trajectories in the possible space, so it gets interesting. But what was the breakthrough? Because this method is actually known as reinforcement learning. I mean, I'm sure you know all of this. And the Turing Award, the highest prize in computing, like the Nobel Prize in computing, was given to the inventors of reinforcement learning just last year. So I was actually at their award ceremony because I got this other award, which is like the mini Turing Award. So cool, good. That's nice. But what is the breakthrough that happened here? The breakthrough is not reinforcement learning itself, not that strategy. The breakthrough is we use deep neural networks to build the pi function and the v function. That's what Google did back in 2017. So it's nearly 10 years ago. Why am I talking about this now? Oh my God, 10 years ago. It's even older than 2021. So this guy must be crazy telling us all these old things, because that is going to be the foundation for how language models will learn to reason without human involvement. Because right now, what language models do is all based on human data. Like every single thing that these models, not all, but most of it, let's put it this way, because this already started. So most of it is based on language models seeing data on the internet, and most of that textual data on the internet, at least the old one, was generated by humans. Right? At least when we started back in 2016 with training big transformers, that was all human data. Good quality, bad quality, terrible quality, of course. So what this does, this allows machines to generate new data that is reasonable, and now these machines can actually continue from what the humans taught them to learn by themselves with this strategy. And this is called RLVR, reinforcement learning with verifiable rewards. And I will get to this in a couple of minutes, but this is going to be the next big thing, right, after LLMs. Okay, cool. How does this work? Well, actually, what you do in these neural networks, you evaluate this pi and this v function with a simple neural net. At the time, it was a super simple multi-level perceptron. That was nearly trivial. Everybody was surprised how powerful that very small MLP was. I was like, oh my God, this is crazy. And so one of the guys who actually did this, one of the authors is a friend of mine, and he told me he was surprised himself. Right? So that's David Silver is his name. He's at Google. He's one of the co-founders of DeepMind. And I had long dinner with him discussing this, and he was like, yeah, I was also not sure that this would work. So the humans inventing this, they don't know whether this will work or not. Right? This is another interesting insight. When we trained the first version of the GPT models, we did not know whether they would work. Right? But we invested in it and it did work. So what you do is you do the Monte Carlo tree search, and this is a very known technique. And then you go deep on this, and you simulate a whole lot of different options. So take that aside. Now what we have is we have reinforcement learning on these states. Right? Now all of us have used a language model. And now you may wonder, well, how the heck would I use a language model to do this? Because a language model works on text. Like I type in, please help me to find my route to the airport or something like this. How does that translate to this? Well, I want to start with a simpler task that a language model could not do about 5 years ago. The task a language model could not do is sort numbers. It could simply not sort numbers. The reason why it couldn't sort numbers is relatively simple, because the way a language model works, it's simply a completion task. It completes the prefix you give it with the next most likely word. And of course, if you now base it on the internet, it's great, because if you now start a sentence like the capital of France is, and then you ask for the next likely word, you will totally get Paris, because in the corpus of the internet language that we have created as humans, most of the next words, when we look for the prefix, the capital of France is, will be Paris. Right? This is how the first generation of language models actually work. They literally just gave you the most likely completion. In fact, today, and I'll talk about this in a couple of minutes, transformer models like ChatGPT, the underlying technology of ChatGPT and Anthropic's Claude and all of those, they still do that at the core. They still simply produce the next most likely word. There's a lot of tricks at the end, though. So we would go into much more detail to figure out what it really does, but at the high level, it's the next most likely word. So here is a problem, of course. If it says sort the numbers 2 and 3, I think it would be fine, because maybe somewhere on the internet there is the text sort the numbers 2 and 3, and then it says, yeah, the sorted version is 2 and 3, right? But if you have a sufficiently long string of numbers, it's very unlikely that somebody on that internet will have exactly asked or will have exactly have that numbers to be sorted, right? And followed by the sorted sequence. So the first language models completely failed with this, utter failure. And you may have seen this a couple of years ago when everybody was like, oh, my language model can add 2 plus 3, but it cannot add 2,135 plus 5,776.67, because the most likely completion task didn't do that. So now we needed to get reasoning in those models. So how do we do this? Well, you can do the same thing, as I just mentioned. You can take a string, a task, like sort the numbers, and what you do is you ask the language model, how do I do this? How do I sort numbers? And then the language model gives you some answers about a strategy how to sort numbers. And it could say, for example, numbers are blue, which obviously is pretty stupid. But these models are not very smart at the base, so this is actually realistic. But then it could say, look up quicksort. Huh, may be an interesting one. Or it could say sorting is simple, which is also kind of not helpful. Or it could say split it into two sets. And now you could ask the same model, how likely am I going to solve the task of sorting the numbers if I assume numbers are blue? Well, that's a very low probability because, I mean, the model will know itself that it has said nonsense. But quicksort looks good. Splitting into two balanced sets looks good. And then what you do, so quicksort is a sorting algorithm, right? So what you do is you then look up quicksort, right? And then this is how quicksort works. But then you realize, oh, you know, I only have these 7 or 8 numbers. This is probably too complicated, so my chance of winning is higher if I just go splitting it into balanced sets, because that's an much easier task than looking up quicksort and running quicksort. As a human, you would never use quicksort for this, actually, right? Obviously. As a human, you would just look at this and say, oh, yeah, sure, I know the smallest is 2, 3, 4, 5, 6, 7, and then 12, right? So that's obvious. Actually, what I just did was bubble sort. It's even simpler. And then you do this, right? So basically, you play the exact same game as we just talked about, just with text. And the only difference that you have is really the function now. The pi function is an LLM. You have to not ask, the next possible move is actually a string that comes out of your language model. And the value function assessing whether the move was good is another language model. And what you can now do is you can encode arbitrary tasks into this, and you can ask the language model, please go and solve this without any additional ideas, but the language model comes up with the ideas itself by querying the policy function. What is a good idea, how to move this forward? Is this a good state now? And boom, we have invented agentic systems. That is essentially the blueprint for an online agentic system. It wasn't called like this when it was invented, but now agents are everywhere and everybody's like, oh, let's do everything with agents. I think it's a kind of a silly term, but that's a different discussion. The only problem is that with agents, we have way too many of these options and tokens, and so now this is nice, right? Because you can totally decouple yourself as a human, and you can simply say, well, solve this problem for me. It's really hard. Prove P equals NP, or disprove it for me. Go ahead, do it. And absolutely, the language model will attempt this. And if you give it infinite compute, it'll surely solve it, right? Because it could simply explore all possible options, which is, of course, of like nearly infinite size. Of course, it's countable, but it's very, very large. And then if we had infinite compute, we could solve it. And now the only limit we have to run this is compute. Right? That's really the only limit. So, and this is why everybody builds these gigantic data centers. This is why everybody builds these more and more compute-intensive things. This is why the NVIDIA stock value is $5 trillion. Right? Literally that. There's no other reason. And this is why the next big asset is energy. because compute comes from energy, and most people haven't realized this. Yeah, but people begin to realize this. It's all about energy at these days. So, okay, cool. So now, the interesting thing we just learned is basically we have superhuman strategy. We have a computer that is better at playing a strategy game than any human on this planet. Like we just know this. By the way, Lee Sedol, the best human in the championships, after losing that game, he said, I'm done. I will not play Go anymore professionally. He retired from his professional Go. He did not do anything in his career. He's now a professor. So he now teaches other people to reason and think. He's actually a super successful professor. But literally the best human player, he was just, okay, this thing is good. I'll just quit. And what we already know is that the models we use today, ChatGPT and I don't know what, they have superhuman knowledge. They know more about the world than any of us in this room. I would claim they know more about the world than we all combined in this room, right? I mean, you can ask really arbitrary questions about deep biological, I don't know what, and it'll give a reasonable answer. Not always right, but a reasonable answer, right? So factual knowledge is actually quite good. And this was the thing that was, O1 was the thing that was the first model that was invented that combined the two with the technique I just explained. Right, so this technique is extremely foundational, right? And this is why we got the Turing Award for this, we got a Turing Award for this. And so we'll see, maybe the people who combined it will get the next one. Okay, So actually, the thing now you may be worried. Now you might be like, ooh, so we have superhuman strategy and superhuman knowledge. If I put those together, I will have superhuman intelligence, because what do we do as humans, right? We have strategic reasoning and we have knowledge, and we combine these two into our actions, into our uttering of words. So that's literally all we do. And well, you could argue that we have some social component as well, so we know love and all of these things, but it's extremely hard to define what that even means. From a technical perspective, we're just reasoning engines and we utter words and we have knowledge. So social aspects and ethics are very hard to define, and so I don't want to get into this. I'm not saying it doesn't exist, I just don't know how to clearly define these things. But now, let's play this game, so we have a couple of minutes time. This is one of the most fun games. Does anybody know this? Anybody know these kinds of games? Okay. What are they called? Exactly. That's the ARC challenge, the Advanced Reasoning Challenge. This is a game that was designed to be a benchmark for machine learning models to see whether these machines can ever outdo humans. And it was designed to be culturally oblivious. So in some sense that any human on this planet, if the human is from Africa, if the human can read or write, if the human is, I don't know, from Antarctica, are there even humans there? I don't know. But if, no matter what, if an alien drops on this planet and can see this thing, should be able to solve this, right? So it's really, really easy, and many of you probably already see the pattern, right? What you have to do. So it's something that I played a lot when I wanted to fall asleep, because it actually keeps your brain engaged, and it's also boring enough that you'll fall asleep after a while. So what you do is you look at these blue and red things, and you figure out what the input to output relationship is. Like literally anybody can play this. You don't need to speak any language, right? You see here, oh, it looks like there are arrows connecting this. Not arrows, but lines connecting this. Okay. You have another example, you have another example, and there's a whole lot of examples, like thousands of those examples to play. AI systems were basically got a 0 score on this until 2023, when these reasoning models was literally at 0. Humans are at 78%, like the average human is reasonably good. Doesn't solve all of those, but is reasonably good. So I'm at 50%, I'm not very good at those. But as I said, I fall asleep with them, so it's a perfect game. Then came these reasoning models that I just talked about. They totally ruled this thing. They went to superhuman performance within 4 months, right? And this surprised famous mathematicians, and everybody was like, oh my God, math is over. Even a funny side story, by the way. So Amelie mentioned that I received this prize in computing last year. So I was invited to the Heidelberg meeting, which is the meeting where all of these Turing Award winners and winners of important math and computer science awards meet. Right? So I was there with all these mathematicians, all these Fields medalists, and it was quite interesting. So one of those people gave a talk. And I gave my talk, a similar talk to this one. Everybody was like, yeah, reasoning models, it's okay. But then basically the next guy came and said, we are done as mathematicians. Because you can use that to, he independently, so he wasn't referring to my talk, but he independently explained how you can use a method like this to actually solve all of math. And then the mood in the room was like, there were all these young people. They were looking up to the big award winners, right? Looking for the future, and they were like, ooh, what do? I'm studying math. So that is an interesting one, because you actually most likely can solve much of math with this. But this is the future. But now, can anybody tell me how many boxes will be colored blue in that example? Because here it's 2, here it's 3, there it's 1, right? Give me the number. Actually, I have to look at it myself. I didn't check this for a while. Okay, I think I have a number. Who can give me a number?
7.
7. Anybody else has a different number? Actually, I don't know. Why do you disagree with me? Let me check. 1, 2, 3, 4, 5, 6. I think it's 6, though. Is it 7? Is somebody seeing a 7th? I think it's this guy, this guy, this guy, this guy, this guy. Right? Okay, so The good thing is, the best AI system failed with that example. So we still have a role as humans. So we can still at least collectively solve that example relatively quickly in minutes. And by the way, playing these games is going to cost many dollars in terms of compute time, because it actually, the system wastes more of its cycle. So we are much more efficient also as humans. So keep that in mind. So we are not done yet. Okay, so there are still tasks that we can do as humans that the AI cannot do yet. Okay, but then I wanted to go a little bit more into the recent past. So there was just a press release yesterday. I'm sorry, that was actually the day before yesterday, because I made those slides yesterday. So, and I didn't think that I would be presenting them today, so 2 days ago. So what happened? OpenAI, a company we all know. I mean, if you don't know OpenAI, it's the company that kind of invented ChatGPT, that's running ChatGPT. No, actually not running it, because running it is in Microsoft, and I'm affiliated with Microsoft, so I'm also affiliated with that stuff. We released, and I'm saying because I was involved in this, we released a new, big bang press release. A supercomputer networking accelerates large-scale AI training. So what people do these days, we build special systems to run extremely large data centers. So what does extremely large mean? Actually, here in this case, this system is designed to connect 131,000 GPUs. And these are not the little GPUs that you have in your laptop. These are the Tesla-style 10 to 20,000 US dollars per piece GPUs, right? So think about the volume and the cost and the size of these systems. Actually, that's how it looks like. So that is now an AI training data center. And you can, that's a truck, right? That's not a normal car. That's not a car like I got the rental here in Spain. All these cars are very small compared to the US. That's like a US about two times the size car that people drive here, and that's a full-size truck. So you can see these things are gigantic. And these are rooms full of GPUs. There are 2 of those. They're connected through the middle. The topology and everything is described in this article. And so that is the infrastructure we are building today to train and work with these models. This uses gigawatts of energy, right? So this is a very large energy thing. If you care more about this, you can actually read how the whole system is connected. The network in this paper that was just released yesterday. So here, as I mentioned, I'm one of the authors somewhere here at the Microsoft site. So huge inter-agency, inter-industry collaboration going on. So, and that's what I wanted to give a little bit more of an insight here. What are we doing as humanity? Because most of us don't know what is actually going on building these extremely large systems. So what do we mean? So what I just said, these language models, they run on these gigantic machines. So we built these gigantic machines. These machines, like the one I just showed here, the thing at the bottom, these machines are called supercomputers because they're bigger than, I mean, you know, supermarket, you know, it's like a market, and then a supermarket is a bigger market. And then if you're in France, they have hypermarkets, which is even bigger than a supermarket. I'm not sure, do you have hypermarkets in Spain? Yeah. That exists, yeah, because even in Portugal, okay. Okay, yeah, exactly. So we have no hypercomputers yet, okay? So we are stuck with supercomputers. But this is literally what was happening in the past. So we pledged a whole lot of money into building larger machines to do this. I was involved in the Microsoft thing. So Microsoft back in 2019 put $1 billion into developing new supercomputing machines. So fortunately, I was part of that program, which was great because it enabled me to look at all these things. But what do they do? What do these supercomputers actually do? What they do is they take the text off the internet. We have a lot of text on the internet, right? They run it through a model that many of you know how it works, right? So that's a standard transformer model, and I can explain that in great detail if you want. We can actually spend a whole day just explaining how that thing works internally. But that model is literally a function f of x. So it takes this input as x. It runs a complicated function on. In fact, this function is so large that it requires an extremely large machine to evaluate it. This function is my language model. This function, if you use your language model in your laptop, you may be using Ollama or something like this. This is what you download. These weights you download, the 40 gigabyte or something that come flying, is that function, right? And then this function gives you an output, which is the probability distribution of the next most likely word, right? So and now you look at this, you read this, and as a human, you're immediately, yeah, of course, it should be harm, and you see the language model is not too bad. In fact, this output vector for any real language model is of size 70,000 more dimensions, because the next possible words are 70,000, including all kinds of Chinese characters and stuff. In Western languages, there are not so many words, but it's also not really words, it's tokens. But let me not get into too much detail. If you want to understand the difference between words and tokens, I can explain. It's really, really easy in case you don't know, right? So in the English language, for example, we have these standard endings, like something is happening, I am going. So it would be totally stupid to store happen and happening and go and going. Why don't I just store happen, go, and ing, right? Then I already have many, this ing is attached to many, many different things. And you see how this works, right? There's shared subwords in the English language. And it really depends on your language. Some languages have this feature of shared subwords, like in German, for example, with concatenated words. It's interesting, in German you can make arbitrarily large words by just concatenating words. And so each language is very different. And so what they do, basically, or what we do in this language modeling is we just look at the most common sub-pattern in the whole text. Is called BPE, byte pair encoding, in case you're an expert, right? And that's what a token is. But typically it's like a word. Easy, when I say word and token, it's kind of the same thing, but it is typically a word. And now the interesting thing is what you know is you have this text, because it's a text from the internet, you know what the right word was, right? And what you do now, during what's called pre-training, you actually update the layers, or you update the weight of those layers to adjust to it. Right? I'm assuming you have kind of basic machine learning knowledge, so that you know what a layer is and a weight. But now the fascinating thing is that the latest model level structure. Oh, sure, I should update this because last week DeepSeek V4 came out. So this is a slide from a month ago. I'm sorry. I should have updated this yesterday. But Kimi K2 was the best model a month ago. Last week, again, the Chinese released DeepSeek V4, which is better. That was trained on 15.5 trillion tokens. Think about it. How long would it take you to read 15.5 trillion words? Well, you wouldn't manage because you would pass away before that, unless you're a very fast reader, but even then it would be unusual. So basically, they train on the whole internet at this point. The number of parameters in this Kimi K2 model is 1 trillion. So it consists of 1 trillion tunable numbers to remember these words. Because as I mentioned, all it does is it represents a probability distribution of the text on the internet. Right? And it has 1 trillion numbers to represent that probability distribution somehow in functional form. We don't know how this really happens, but we know it does it. Right? That's the funny thing. So we are, by the way, what I always like to say, we are right now at the stage where the Romans were when they built bridges. The Romans understood I can build an arch, and when I close the last stone in the middle, the thing does not collapse. Right? The arch holds. Arches are fascinating because how do you come up as humans with the concept of an arch if you don't know gravity? Right? It's extremely hard. Because you need to come up with this, oh, I put this together, and then I put the last stone, and then it just holds. This enabled building very large bridges. This is what, okay, not the size of today's bridge, like hundreds of meters, but they could build 60-meter bridges with this, which was unthinkable before because there was no single object, like no tree long enough to actually do it. So they built these arches. And they did not understand gravity. Later we understood gravity. Now I can explain in a physics class exactly why an arch holds. They did not know. We are at the same right now. We know that the thing functions. We have no theory of the information processing inside the thing to understand why it functions. Right? That is fascinating. And I think that we could actually understand this. But I'm not 100% sure. And now the problem is if you want to go and do interpretable machine learning, you would need to understand how this thing works internally, right? So somehow, because black box methods, I always say, if you use black box methods, you could have used these black box methods with humans for the last 1,000 years, because our brain is also, you could argue, also a statistical language representation machine. Am I just following the most likely probability distribution of language here? Yes, because my sentences make sense to you, I hope. My sentences make sense to you. If I would not be following that probability distribution, I would be talking gibberish, like a bad language model. So keep that in mind. It's an interesting way. Am I a language model? I don't know. But then anyway, it takes an extreme amount of resources to train these models, right? Okay, so now the silly thing is that these resources are getting really expensive. So we are actually today, to achieve more, and this is a unique situation in human history, we are only bound by the amount of energy we can turn into information processing to achieve more human progress. It's not about materials or tools anymore. We are gated by the amount of information processing we can do. Because we understand algorithmically that we can achieve anything with these tools. We're just gated by the amount. So now we need to optimize. We need to optimize two things. We can optimize these language models to be better, which is what many, many people do. Like to use less tokens to achieve the same goal, which is a really large field. And as you can see recently with the pricing of those APIs, for example, Claude had kind of an unlimited token budget until people used agentic systems, what I mentioned before. And then boom, you now have to wait every 4 hours to gain more tokens. I don't know, if you're a Vibe programmer, you know this, it's terrible. People stay up overnight because every 4 hours ticks at night as well. So I have many friends who are really hurt by this. Or the second thing you can do is you make the compute system more efficient. So you can use less tokens, or you can make the generation of a single token more efficient using less computing. Right? That's what I want to talk about in the remaining time. I want to talk about how can we achieve that we make each token more efficient. Getting less tokens, by the way, is also a super interesting observation. If you are selling an API, if I'm Anthropic and I sell you Claude as a service, I am not interested in minimizing the number of tokens I'm using to reply to your request, because you are paying me per token. I'm actually interested in giving you longer answers, because then you pay me more. So that is a very interesting observation when you, okay, we can go into details in the break if you want, because there's a huge economic implication here. But what I want to lead us along is really trying to understand how we make things more efficient. And another reason why we want to make this more efficient is that these models are growing like crazy. So this is the good old days, 1960 to about 2015. There was a very low growth in the compute requirement of those models. It was basically following the natural, like my computer gets faster every 18 months, Moore's Law style thing. So nobody was willing to invest more money into computing for machine learning or artificial intelligence. That's the baseline. So here, this is really following the line of my computers get naturally faster. What happened here? Well, there was the invention of modern AI. And then now everybody, and this is a log scale, so this is completely crazy. So everybody is now willing to invest more money. As I said, it's the largest infrastructure built out in human history. So in many places, if you look at the worldwide average, the human investment relative to the GDP of what we actually produce in AI is among the largest. If you just look at the United States in human history, if you just look at the United States, does anybody know what was a larger project in the United States that was relative to the GDP where the investment was larger? There's only one. Anybody can give me a guess?
NASA.
Sorry?
NASA.
I didn't get it.
The space.
No. That was cheap compared to the GDP. NASA was never funded that well. The Manhattan Project is quite up there. Was more expensive than NASA, but not there. No. It's actually, we exceeded the Manhattan Project already today. By the way, the US government, they announced a Manhattan 2 project for AI. Didn't happen as far as I know. It was the build out of the national railroad system. That was more expensive. Like the universities like Stanford we know today, they were conglomerates building railroads. That was extremely expensive. But however, in next year, if the growth continues like this, next year the infrastructure growth for AI will outdo the railroad system. So then it's definitely number one. Another interesting fact is that just Microsoft alone invested $32 billion into AI infrastructure or cloud infrastructure just the last 3 months, just the last quarter. $32 billion. That is more than the GDP of many countries in that area. So I should have checked what Spain is. I would guess it is there, right? So it's an interesting question because it's only 3 months. Okay, so Now I want to go a little bit more into detail on the technical side, so this was still on the motivation. By the way, if you have any questions, as I said, I can diverge arbitrarily from the slides. It has a down and an upside for you guys, because I will then not have a good red line if you diverge me. I'm happy to do this. But the upside, maybe it may be more interesting for you. So if you find the slides interesting, we can go with that. If you have any other questions about LLMs or reasoning or stuff like this, I can go into tangents. So please don't hold back. But for the remainder of this talk, I want to give you definitions, which I find quite important because we need to speak the same language. So one definition is when I talk about performance, I mean compute performance. Because many machine learning people, they often use accuracy. They often use performance for how well a model actually does solve tasks. In my terminology, performance is compute performance. When I want to talk about how good a model is, I talk about accuracy. Okay? So these are two different terms, and this is very often confused. When I talk about quality of a model, I also mean accuracy, essentially. Right? These are both data science terms. Performance is a compute-centric term. When I talk about pruning, which many people may know, I mean that you can remove weights in a network to shrink them to a smaller size. This is a subset of sparsification. So sparsification is a more powerful concept that many of you are familiar with. I just want to make sure that we are not getting confused here, because now it's going to be a little bit more technical. Okay, cool. So yeah, in case you care about these numbers, you can find them. And I hope the slides will go online somewhere later that you can find these things in case you want. So now the first thing I want to get clear is that many people just think, oh, the last 40 years were wonderful because there was this thing called Moore's Law, where, who knows Moore's Law? Okay, so it's about 10%, I would say. So Moore's Law says that every 18 months, the number of transistors in my chip doubles for free. That's what the original Moore's Law said. So literally, if I just wait 18 months, I will get a chip that has twice as many transistors for the same price as I got the one before, at the same energy consumption. That has happened for 40 years. Not kidding. For 40 years, we were writing Moore's Law. So basically, every 18 months, Intel cranked the crank, and we got a better chip twice as fast. And then, of course, companies like Microsoft immediately consumed that speed to give you more complex operating systems like Windows. And so this is what happened. So you can see this here from 1975 until 2015, approximately. As I said, 40 years. It's more like 1973 or 1960 something to 2007, because 2007 something changed. Moore's Law slowed down. What was the reason why Moore's Law worked so well? I mean, first of all, one thing changed here in 2007. Another law that most people don't know, it's called Dennard scaling. Who knows about Dennard scaling? Most people don't. Okay, you learned something new in this talk. So Dennard scaling is that gentleman. So by the way, Gordon Moore was one of the founders of the company Intel. I mean, many of you know the company Intel makes these CPUs, right? The blue logo with like, okay. Dennard was at IBM, another company that made computers. And Dennard basically said, it's another law. Whenever I shrink the size of my transistor by half, the energy consumption of the transistor goes down to half, which is extremely important because the only reason why Moore's Law happens is we made these transistors smaller and smaller and smaller and smaller over time. So the energy consumption followed of these transistors. So what did that mean? If the energy consumption follows, then my energy budget per chip is about the same. Right? When I shrink them by half, energy goes to half. I get twice as many, so it's great. I still have the same chip size. Why is that relevant? Yeah, because the problem is that I need to cool these chips. Do I have this here? Yes, the typical watts. A chip is like this size, computer chip. How many watts can I take from a piece of silicon of that size before it melts? You see that? It's about 200. Because here it stops scaling up. So early chips use very little energy, but then they stop at about here because there's no way to get more than 200 watts out of an area like this before the thing melts, because the energy density at this point today is the same as in a rocket nozzle. You know, the thing that drives a rocket. It's the same heat per square millimeter. And there's no way that I can get more out of this before my chip melts. I mean, there's liquid cooling and all of that, but that gets you another 50% or so on top of this. So Now, unfortunately, what happened in 2007-ish is Dennard scaling stopped. Moore's law continued, actually. I mean, the transistors got smaller and smaller, but due to quantum mechanical effects, they got so small because what they need to do is they need to insulate. Right? Remember, what a transistor does, it turns off and on. So it needs to insulate electrical current. And if your layer that insulates you from your neighbor gets smaller and smaller and smaller, and at some point only 10 atoms wide, you have quantum effects that these silly electrons, they just tunnel through because the barrier is not big enough anymore. And that's what happened here. So we get the things so small, like single nanometers today, that they don't hold anymore. So the Dennard scaling stopped, that's a problem. So Moore's law is dead. And what happened really, we went from a very large, these are transistor pictures, to smaller and smaller and smaller and smaller transistors. So today we're at 5 and 3 nanometers, but that's kind of fake. And then we couldn't hold it anymore. Right? So we they don't hold the charge anymore. They do, more or less, but it comes at a larger energy loss cost. Okay, cool. So that's part of the problem. And we can go into much more detail, but for this audience, I would say that that's enough to understand that in at least the way we built computer chips the last 40 years, there is no way forward to make them faster. Like we are stuck. And that's unfortunate. It has been lasting for 40 years, and now it's over. The only way to get faster chips today is to go to completely different technologies. Either we could talk quantum computing, I could tell you all about that, but we don't have enough time. We could talk about neuromorphic computing, we could talk about analog computing. None of those is at a level today where we could actually use them for anything useful. Like we are still using the standard chips in your phones, in the data centers, and that's a problem. Now the only way to get more compute, as I just mentioned, humanity's progress is limited by more compute, right? We need more compute, but the only way to get more compute is build bigger data centers and invest more energy into them. That's a very sad statement, right? So maybe we really hit a limit. We don't know. And this is why, again, I want to motivate you to listen to me more about talking how to make these models more efficient, because we cannot just wait 18 months and they will be faster like we did the last 40 years. Actually, it was a very nice time. Optimization didn't play a role because we were just like, okay, yeah, we'll wait and it's going faster. So now one way is to use smaller models. As I mentioned, these models have trillions of parameters. Why wouldn't I just use millions of parameters? Well, the unfortunate thing, what I had to skip in this talk for time reasons, is that the only reason why language models are so powerful is because we scaled them up in the first place. Right? We started with small models, and now we went to trillion parameter models because you need a certain capacity in the model to learn the probability distribution of text on the internet. That's essentially what it learns, as I mentioned. And now the option space for next words given prefixes is very, very large. And it's even funnier, it is a very fuzzy problem. Because if I want to complete the following sentence, Torsten is, you could complete it in many different ways. Right? The next token, actually there are many probable tokens like stupid, entertaining, dumb, or whatever. You can make up the any next. That's all plausible. They're all plausible words. Right? So smaller models will not be able to represent this option space that is fuzzy and extremely large. Right? So these models that seem extremely intelligent today to us, they're nothing but statistical text completion engines in an extremely large space, like trillions of parameters. This is what's really happening behind the scenes. So downsizing may be possible, but is actually one of the harder ones. So. And there is a microchip. And so we can have operator factorization. That's a little bit more of a technical detail. The funny thing is what these models do is actually they work on linear algebra spaces. They work on Hilbert spaces, actually. So there are matrix multiplications. You take a vector. Your word is represented by a vector. Again, if you care about this, I can totally explain that in detail, but let me stay at a high level. So each token or each word is a vector. And what they do is they project this vector into different spaces, and this is how they work. So now, each matrix vector multiplication, which is what's happening in those models, together with some nonlinearities, each matrix vector multiplication implements the transformation, or what many people call reasoning, within that model. Okay? Now, how does that work? Now, what we could do is we could now see the matrix itself as an operator. Because what does a matrix do? It's a basis transformation. Right? You take an input vector, you multiply it by it, and after that, the vector is represented in a new basis. Like if you know linear algebra, you probably learned this in your A levels, right? So great. Does anybody can do this? Great. The only thing is these matrices are very large. They're like 12,000 dimensional, and then it gets extremely hard to reason about what's actually happening. We could factor these matrices into two smaller matrices to represent the principal component, for example, of this basis transformation, such that I'm maintaining the gist of what's happening in this transformation. Right? Many of these matrices actually can be compressed quite well. Operator factorization is one way to compress it. So you take a single matrix that is n times m, you decompose it into two matrices, A and B, and each of those is n times r and r times m. This is lossless. If the rank of the original matrix is r, then you will not lose anything. Unfortunately, for real training matrices, the rank is usually full rank, so which means the rank is either n or m, whatever is smaller in this matrix. So this is an interesting scheme. I will not talk about this. This is a mathematical trick. If you're a mathematician, you will totally love this. You will do this, you will realize in practice it doesn't work that well. So in theory, this is great. One thing that is super successful, what most people do today, is called value quantization. So you take, and this is now a very foundational principle. When we compute these models, I did not tell you how we compute them yet. I told you there are 1 trillion parameters in these models, right? So there are 1 trillion numbers. A parameter is a number. But how do we represent these numbers? Because in a computer, we need to represent these numbers somehow as ones or zeros, right? We all know this. They're so-called binary representations. So most people, when we started training, used 32 bits per number. So a so-called floating point 32 value. Right? So this is a mantissa and an exponent, and I hope most of you know how that works. So we have a number that's represented by 32 bits. But now you may wonder, well, actually, is 32 bits enough? Well, yeah, it worked, so it's enough. But is 32 bits with 16 bits be sufficient? Or could we do it with 8? Could we do it with 1 bit? One question to you is, and do we have any biological person? Our brain is also a binary computer. Right? So we have these neurons and these synapses, and we understand pretty well how they work today, and they fire. Right? Firing basically means I'm sending a 1 along a line, and not firing means I'm sending a 0. I mean, I'm not sending anything. Right? So we are an asynchronous system in our head. So now, so I'm putting a 1 on a line, and then there is a receptive thing in our brain that receives inputs, right? Because it's a network, it's a neural network, essentially, right? So the input comes now from multiple different signals. How many bits does the human brain actually compute with? Does anybody know? Does anybody have a guess? So what you have, and let me just finish the explanation that everybody can follow. What you have is you differentiate, well, it's an analog system, right? When a neuron fires, it puts a certain voltage on a line, and when another neuron fires, it puts another voltage on a line. These voltages are added up when they get to the receptor, and so how many different voltages can the receptor distinguish? You can measure this. You can cut a brain open and attach probe, so I don't know how they actually measure it. But you can somehow measure how many voltages you can distinguish. Yeah, so what's your guess?
Well, my guess is that it's variable and it will depend. I will guess it will be something like the brain. I expect it to be something like an optimal length or optimal coding for like encoded with little bits and really complex signals for way more big. So be adaptive, which is something that neural networks are not right now.
But there is still a range, right? So we're probably not at 100 bits. So what would the range be? I agree, there is a huge variability, but if you measure the average, any guess? Yes?
Could it be 40 to 120 bits?
120 bits, no, that is
120, 40, depends on what unit.
40, no, that's too much, that's too much.
Too much?
Yes, it's way too much. Our devices are not that good. I mean, mine is not that good. Yours is better, I'm sure. Anybody else? Yes?
Around 20.
Around 20 is still too much. I'll give you. So they measured that we can distinguish 24 voltage levels on average. So the log of 24 is 4.6. So I am a 4.6-bit computer, essentially. You were probably at 5 bits, or not. But none of us is significantly more than that. So why do we compute? Why do we represent the values in deep neural networks with 32 bits? Well, we don't know. So what a huge gain is today is we shrink for each of those numbers that we represent, we shrink the number of bits. Today, it's standard to compute, to train models at 16 bits. Everybody trains at 16 bits. Nobody trains at 32 bits anymore. Some values are 32 bits, but not all. If you download an OLAMA model to your laptop, you're most likely using an 8-bit version. If you're doing the highest compression, you will be using a 4-bit version. Now it gets interesting, right? So we say humans 4.6 bits, so we're already below that. Actually, the most modern quantization algorithms, which we release with partners, they go down to 2 bits or even 1 bit per weight, but they're very advanced, so they do very strange stuff. So this is extremely valuable, this quantization, but I'm not teaching you all the details here because this is done. I mean, we understand how to do it. So it's pretty clear that you cannot go much below 1 bit per weight because, I mean, what is it if it's not on or off? The way you can go beyond 1 or below 1 bit is you just consider multiple bits in the same space. Right? So then you can go below 1, but it's minor. So we're at 4 bits, and 4 bits is kind of the minimum reasonably we can achieve. I can even prove this that information theoretically there is something to 4 bits, but again probably too much for here. But it's super important. Like anybody does quantization. Like you train your models in higher precision, and then you quantize them down to super small, like usually 4 bits or 8 bits. Another thing you can do is you can just apply standard bzip or zip methods. You can just compress it with your I don't know what you like, zip or something. That is usually terrible. That does not work. But you could. One other thing is parameter sharing. You could now think about, could you use the same parameter for multiple places? Yes, there's a question. Yeah, excellent.
So with the optimization of the models, how are we benchmarking the trade-off between the efficiency and the accuracy?
Exactly. That's a very good question. So the question is, I can repeat it. The question is, when we let me rephrase it. When we compress these models, when we do any of these things, we're going to lose accuracy of the model. Because obviously, if you compress too much, the model gets too dumb, right? And now there is a trade-off, right? Because otherwise you would just go to 0 bits and be happy. So obviously, as you compress, the quality goes down. Absolutely. The question is, how do we assess this quality? There are many metrics. So for example, this one standard metric in training is called perplexity. So perplexity is a metric where, remember, you do the next word prediction, right? And now there is, you can of course measure what your hit rate of the next word prediction is with respect to your actual training corpus. Because you can look at the statistics of the training corpus. If I say the capital of France is, and the model says washing machine, not good. If you say Paris, oh yeah, check. So you can now measure how often it hits that, right? And this is a very simple statistical technique. That is not very indicative of the smartness of models, which is very funny. A model can be a perfect next word predictor, but not be very smart. So to get to the smartness, there are these real-world benchmarks like MMLU, HelloSwag, there are GSM8K. There are many benchmarks that are typically multiple choice questions, which humans have designed. So for example, Mary has an apple, Peter has a pear. How many fruits do Mary and Peter have together? Option A, 15. Option 2, 2. Option 3, 1. Option 4, 96. And then the model gives you 1, 2, or 3 as an answer. That's MMLU, essentially. There are 100 or 200,000 of those questions, and if the model answers them right, what's the percentage of the model being right? Does that make sense? And then you compress your model, you benchmark it on these question sets. If it's still good, you're happy. You compress it more. The moment it degrades, you're unhappy. What we do in production and in practice is we typically say 1% loss is okay. If we exceed 1% loss, then we are unhappy. So what we can do is we can compare to a full precision model going to 4-bit, we can lose less than 1% on MMLU on these question-answer data sets and still go to this bit width, which seems reasonable, right? I mean, 1%, I'm sure it's in the noise anyway. Does that make sense?
That makes sense.
Yeah, so it's a very clear benchmark.
I have another question, if I may.
Of course.
It's more of futuristic maybe and towards governance. Are we going like with the accuracy or the trade-off? are we going to reach to a level where we are going to have a monetary metric on that, let's say per accuracy of per a barrel of oil or a joule or a dollar value?
Yes, we indeed have that today. I mean, the way, for example, internally at Microsoft, how we measure these things is the cost per token generated. So you can measure, if you know the cost of your machine, right? You know how much you paid for it, you know how much you paid for it initially, you write it off after 5 years or something like this, or maybe 10 years, I don't know, that's a business decision how long you run these things. You know how much energy it takes to produce a token, you know how much energy costs. So now each token, you have so many tokens per second, and from that number you can now compute how much it costs you per token. That's usually in the like fraction of cents, of course, it's a very small amount of money per token. And then you can compute exactly what the economic impact is of generating these tokens. That is the main optimization. All of that is basically expressed in this. It's just that it's extremely complicated to get to these real dollar or euro values, depending on where you live, or AED, Riyadh, what do you have in the UAE? Exactly, thank you. So it's very hard because the price varies greatly depending on who you are. NVIDIA will give you a very different price, for example. Does that make sense?
Yes, it does.
Yeah, so you can compute it for every real system, and people do this very much in practice.
Thank you, sir.
So now, the last thing, any more questions?
No.
I love this. I mean, if you have, yes?
About competition and other parameters.
Yeah.
If you quantify to 8-bit, for example, there is any relation between two parameters at 8-bit and one parameter at 16 bits?
Oh, I see. So you would say that you wanted to quantize them, each parameter in a different bit width, potentially, to achieve better accuracy.
Yeah.
Absolutely. So people have been trying this, but it's now you have a problem. So we know how, so it's not practical, people don't do this in practice, but I'll explain you exactly why. So remember, you have 1 trillion parameters. It's a large number. So and now you need to remember, if you now have some parameters in 16-bit and some parameters in 4-bit, you need to remember which parameters is in 16-bit and which parameters in 4-bit, right? If you have this in 1 trillion out of 1 trillion parameters, how many bits do you need to remember the offsets of these parameters? Oh, it's a disaster, because 16 bits or 4 bits is only 16 different values you can differentiate. So just the meta information for remembering what is more expensive. So now you could now say, okay, I can encode it in every value, right? I could just mark the value itself, whether it's 4-bit or 16 bits. That requires 1 bit. As soon as I allow you 4-bit, 8-bit, 16, 32 bits, it needs 2 bits. And then you already have half of your budget for just remembering what is going on. Yeah. And now you see where this is going, right? Yeah, yeah. The 4 bits are so small, you have basically no freedom remembering any other information because you'll need at least 1 additional bit, which is already 25% of your budget. Oh, that's terrible. So what people did, what we actually invented at Microsoft a long time ago, is another cool method. It's going a little bit into detail, but you seem to like that detail. So what we do is we say, well, you know, we take 16 or 32 of those numbers together, and we mark them as 4-bit or 8-bit. And now we have a nice block of those. So the relative overhead goes down because we already have 32 or 16 of those. And then we put them together with a scaling factor. This is today supported in hardware. So what's called NVFP4, NVIDIA's FP4 version, is indeed 16 FP4 numbers together in one block. You cannot use them separately. Like they're different values, but they're processed as one block, together with an 8-bit scaling factor. MXFP4 is basically the same thing, just of a block size of 32, so slightly more efficient. Does that make sense? It's really about representing these numbers. Your idea is great if you have large number of bits, but for such small, it's getting very hard.
Okay, thanks.
Yeah, sure. Any other questions before I go on? Yeah, please.
If you go to slide 4.
If I go to slide 4, you say?
Yeah.
Oh gosh. Let's see. Yeah, they have a whole lot of animations here. That's the. Oh, no, I think I can just press. I can just press 4. No, I can't just press 4. That's the problem. Can I just press 4 here? No, I can't. Okay, well, I'm not good at PowerPoint. This one. Yes.
So we say value function is another LLM trained on known examples.
Yes.
So does this mean that we are going in a direction where the supercomputer can think like the whole humanity already did, and maybe can get some correlations that usually a human cannot do, but maybe it cannot do something that is completely uncorrelated?
Yes and no. So exactly. The thing is exactly, because you have this gigantic knowledge base, so the computer can now correlate things that a human mind, a single human mind cannot perceive. I mean, we somehow have these great insights where much of it is randomness. So some human mind comes up with a great idea how to correlate two things and then gets famous with it. It doesn't mean that the person was the smartest one, just had a good idea, right? And computers can now automate that. Exactly, that's your first question. And yes, the answer is yes. But now your second question was, can we actually create truly new things that is not in the training data set? And the answer is yes. And you know what? You know why? It's called hallucination in language models. Everybody thinks hallucination is a bad thing. I think constructive hallucination can be a good thing. So what most people say is hallucination is something when I say, oh, the capital of France, I like this example as you can tell. Capital of France is Madrid. And then we say, oh, the language model hallucinated, it's bad because we know it's wrong and blah, blah, blah. We want to avoid hallucination. Absolutely. Even though there will be at least one human on this planet who I will ask this question and the human will say Madrid. Pretty sure. So humans do that as well. So, but now, if I am a scientist, how do I come up with new ideas? I inspire my brain to go beyond my current knowledge, because otherwise it's not a new idea, right? So we need to come up with new ideas. So I could make it, what I usually call is make an educated guess. I come up with a hypothesis. Hey, usually it's going like, let's try that. That sounds like a good idea. Nobody has tried that before, so it may be new knowledge if it's successful. A language model can hallucinate a new idea like this as well, right? Not in the stupid example like with the city where we know the fact. I'm sometimes wrong with facts as well. I hallucinate as well. But I use constructive hallucination to create new ideas. And then the only difference I do today to a language model is I just don't state it as if I'm absolutely sure about it. That's a huge problem with language models. They always state things and they're 100% sure about this until you tell them, oh, I think you're wrong. And then they're like, oh, sorry, yes, I know, yeah, 4 plus 4 is not 16, I know. And then they pedal back, but they state it with absolute certainty in the first case, right? And it's even funnier because they're so abiding to you. If you tell them that a correct fact is wrong, they will still, oh yeah, it's also wrong. This is another problem. But anyway, I'm diverging here.
But still, the hallucination would be something that is somehow in the past archive. So some correlation there and there.
Not really, because like, how do humans hallucinate most if you're drunk? Right? That's just a fact. No, I'm not kidding, actually. If you want to stimulate your brain to create additional knowledge that doesn't really exist, you get into a state of either drunkenness or extreme tired, being extremely tired. Then you will create random things. Your brain goes into a more random mode, which many people do for fun. I'm very creative when I'm extremely tired. I'm not talking about being drunk. I'm never drunk, of course. And so in that mode of operation, you can actually come up with new ideas. Many people say I have a good idea in the shower. Most people don't have good ideas when they focus on things. Most people have good ideas adjacent when you're not focusing. Hallucination. Because this is exactly when it happens. Oh, I'm not really sure about this. I have some random, oh, that's a good idea. Language models work exactly the same way. It's called temperature. You adjust the temperature. If you want the model to be more creative and hallucinate more, you just say, temperature is super trivial, by the way. We've seen this output distribution of possible next tokens, right? When you dial up the temperature, you basically say, well, let's not take the single token with the highest probability. Let's actually consider the top 5 tokens and make a random selection out of those. And if you now make this large enough, it'll be totally random. You'll be just picking random, then you don't need a language model. But if you make the temperature reasonable, it'll be like, oh, let's choose this next token, which is kind of like unlikely, but you know, I'm like drunk, I can go ahead and do, no, I'm sorry, I'm tired. I can go ahead and do these things. Does that make sense? Mm-hmm. So you can totally dial the model. So if I put a model in research mode, I dial up the temperature. Of course, I get more random trajectories, which go into idiotic things, but I may have the one trajectory that is really a winner. That's again where I need a lot of compute. Because what I do in RLVR, which is this reinforcement learning with verifiable rewards, is nothing but taking the model, dialing up the temperature a little bit, and then it generates 1,000 possible reasoning paths, which is extremely expensive. But you just let the thing run. And what you need is a verifiable reward. You need to make sure that you can test at the end whether the result is correct, because otherwise you don't know if it's nonsense, right? But now, there's a nice thing in math. This is why math is pretty much solved. Many math things, I can prove whether I found the correct result. Let me give you an example. If I give you the task to factor two large numbers, we don't have a good algorithm for it. And I'm now telling you, I want you to factor the number 475,776. You will have trouble doing this. I'm sorry, you may. I will have trouble doing this right now. I would probably ask a machine to do it for me, right? The machine would also not be able to do it well because it's a hard problem to factor large numbers, right? Actually, 76 is easy because it's divisible by 2, so that's a stupid example. Pick something that looks like prime. So factoring is a hard problem, but it's super easy once I give you two numbers that are, and I claim it's two factors of this number, I claim this is true. You can easily check it by multiplying the two numbers. There are many, many mathematical problems that have this property that they're easily checkable, like factorization, but really hard to solve. Many NP-complete problems have this property. In fact, NP-completeness, the definition of NP-completeness bases on the checkability in polynomial time, right? Because otherwise it's not NP-complete. So most of our math problems, in fact, are verifiable. So now what we can do is we can just let the language model explore proofs, and then we can prove that the proof is correct relatively easily. And that's what RLVR is. That's what many of these people did, is they solve very hard math problems. They define problems that are hard to solve, but easy to prove correct. They run with the hallucination mode on, essentially. Thousands of reasoning trajectories, let the model go ahead, and if it ends up with the right solution, we say that was a good reasoning path. If it ends up with the wrong solution, we forget that reasoning path. Right? You throw a gigantic compute at this, but what you then get is a new set of trajectories. And this is what we do in RLVR. Again, I keep using that term. It's a new big thing, right? This is what we do there. We train the language model then on those trajectories to use those for the next best prediction. Now you have a self-improving language model. Now you have a language model that solves problems. It's like a human. Like if I'm solving problems, I'm remembering how I solved it if I'm successful. If you now train the model on these successful reasoning trajectories that it randomly generated, the next one will be more successful for a similar problem, right? And now you run this in a loop. And this is what these gigantic computers do. They run this in a loop right now. There are thousands of computers running millions of these reasoning trajectories while we are speaking here, improving themselves to be better reasoners. This is where all this compute goes. Does that make sense? Mm-hmm. It's actually really cool if you think about it. And the human is out of the loop. The human simply defines, oh, that's the problem. The computer can do the rest. And this is what's fascinating. Because actually, I claim the computer today can already create the problem as well. Like, you don't need the human in the loop. You just need the human to turn it on and it'll go away, supply the energy. So that's a little bit scary as well if you think about it. But it is what it is. Make sense? Okay, cool. Any other questions? It's a fascinating field, yes.
So my question is about good hallucination models.
Yeah.
Can we reach like a model that hallucinates in a good way? In the sense, I can go very creative with it.
Sorry, like your audio is too silent. I don't get a speaker here, I think.
So I can go very creative while discussing with an hallucination model. Because as far as I know now, all like big companies are trying to have models that do not hallucinate. Yeah. If I want to reach a model that hallucinates, how I'm gonna have this?
And now we have to get into the definition of what hallucination actually means. So most people use hallucination use the term hallucination when the companies say, I don't want a model that hallucinates, that it makes up things that it should know, right? And again, hallucination is a natural process. Hallucination is a general process, in my view, where we make up things, right? So for example, when I say 4 plus 4 is 18, I'm making up the 18, but I should know that it's actually 8. So that's what most models call as a hallucination. But what I'm asking, if you ask me the question, what is nitrogen nease or something like this, then I would personally not know. I should know maybe because it's a well-known term, but I don't. And then my hallucination may be valid. Like in science, as I said, science is fundamentally a process of hallucination because you need to create new facts that you then prove correct, right? And so now there are these two different kinds of hallucination. The one that most people call hallucination, where I should know better, right? That is the bad one, right? And that's clear. But then there is this case where I don't know, and I should then prove that it's correct. That's what I call constructive hallucination, right? So you don't want to destroy constructive hallucination, but you want to destroy the hallucination that most people call hallucination, right? And now the way to do this is you can ground a model in data. This is what most people do today. You can have the model query databases where this information is just in. So for example, if I wanted to ask what my salary is, it's on the internet, unfortunately. So you could go and now Google and find it in some Swiss public database, right? And so, but of course you could also guess it, right? If you guess it, you may be constructively hallucinating, but if you would be really thorough, you would look it up in the database. So that's how these models behave as well. They can give you a guess, or you can ground them. It's called grounding. You can ground them in real data where they go ahead and actually look it up. And today, when you talk to your favorite language model, it's a mix of the two, because grounding is very expensive, right? If I now make Gemini go and look through all the internet trying to find this is going to consume at least 10,000 tokens. It's not so easy to find, right? Or if I make it guess what does a professor earn in Switzerland, well, I mean, it can give you a reasonable guess, right? Does that make sense? I mean, the grounding is expensive but possible. If you do health, so I'm working a lot in medical applications, for example, you always want to be grounded, right? Because you don't want to guess and have people dead after a while. So it really depends on the importance and how much you want to invest.
But then can we fine-tune a model to push it for good hallucinations?
Yes. This is exactly what I meant with the temperature.
Okay.
So
I mean, my question was this, basically.
Yes. But I see. No.
Okay.
That's the problem, exactly. When you make the model more creative,
yes,
it'll give you about as much total nonsense that it gives you reasonable things. That's the unfortunate. It is not good at educated guessing. So humans are good at educated guessing. So which is actually funny, because before I talk to you, if you make me hallucinate, before I talk to you, I'm thinking about, is this reasonable what I'm saying? Or will I just say washing machine now? But I had washing machine in my head, but I usually wouldn't say it. And that's the thing. Language models can barely internally think. They utter everything comes out. And then, for example, if you look at how your Gemini or your favorite language model works, you can if you're very fast, you can click, show me the reasoning. And if you then read these pages of reasoning text, you will find half of that is, oh my God, what kind of nonsense is this? And then it filters itself. Like it summarizes and it gives you an overview and it queries itself and it does all of that self-improvement. But it's very much like humans work internally. Make sense? Okay, cool.
Let me to have a proposal.
Yes.
Because really your talk has a lot of questions. But
we are out of time.
We have just now the lunch because they waiting us the people for the lunch.
Yeah.
I propose the second part of your talk. If you like, we have after the lunch we have Janelle that is coming. Then a short talk of Oyer. Then my proposal to have a second part near to an hour at 4:45. We have you have at this time the thing the groups, but we can change and to have the second part of Torsten. Can you this afternoon?
I can. I don't know if the
I think it's very interesting.
I'm not sure.
Because you are in slide 10.
We're in slide 10 out of 40. Yeah.
You are in the slide 10. I think it's 1 hour later. It's better to continue. Do you like?
I'm fine. Again, I don't want to bore people to death here with this.
If you are agree,
but I don't have to go through the slides. You know,
we should do the group work by the second part of Torsten, and you are connected and you work along the weekend online the teams. Do you like the option? Yes. Torsten, thank you very much.
Sure.